All right, hello there. This is me from New York. I want to do this quick recording on our Monday lecture on the topic of our chapter 5. And your TA Qing Yang will be with you tomorrow during the lecture. So if you have the time, go there and Qing Yang will host a Q&A session with you. So we have finished our chapter 4 and we're ready to move on applying those relatively abstract concepts and terminologies we defined in chapter 4. Right, so on top of entropy, in our last lecture, we spent some time talking about chemical potential and equilibrium. So for example, when we talk about chemical potential, what we have is defining this chemical potential nu for substance I at phase alpha to be equal to the partial derivative of your Gibbs free energy over the number of mole of that substance I, the change of that number of mole of substance I at phase alpha, while holding temperature, pressure, and all other number of moles of substances constant for the process. Right, so remember our chemical potential is an intensive property. And we linked chemical potential with equilibrium. So for example, if the summation of the chemical potential times the change of number of mole for all phases and all substances, so mu I alpha dni alpha equals to 0, then we say our system is at material equilibrium. We also have other properties that need to hold true. For example, closed system, PV work only, and also constant temperature and pressure. All right, and other things we went over, like the nature of chemical potential as a property. Imagine you have two cylinders containing your substance I in different phases. All right, let's assume on the left-hand side we have mu J alpha. On the right-hand side we have our mu J beta. So now let's say we know this substance J flow from beta to alpha, where beta and alpha are phases of the substance J. So the question is, which phase has higher chemical potential? So here, remember, we say irreversible processes, your substance always flow from a phase with higher chemical potential to a phase with lower chemical potential. So in here, what we can conclude is mu J beta will be larger than mu J alpha. All right. And let's move on to today's lecture. So the first topic here will be to use whatever we just learned and to understand how to calculate standard enthalpy of reactions and also how to get standard enthalpy of formation. So the first one might seem pretty straightforward. So when we're talking about the standard enthalpy of reaction and standard enthalpy of formation, the first thing we want to keep track on is the standard state. So when we are saying something or some kind of substance is in its standard state, what we mean is for solid and for liquid, the pressure is at 1 bar. The temperature is typically at 298 Kelvin. For gas molecules, we're defining the standard state for gas molecules being at pressure at 1 bar at some temperature, like typically 298 Kelvin. And we're also assuming the gases are behaving like ideal gases. Later, we'll also talk about the standard state for solutions in Chapter 9. So what does it mean? It means we can now calculate the enthalpy of a reaction in its standard state, or we can calculate the standard enthalpy of reaction, which is delta H naught at certain temperature. T stands for temperature of the reaction here. So for example, if we have a typical reaction of small a times large A plus small b times large B goes to product small c times large C and small d times large D. So here A are coefficient, stoichiometric coefficients. Right. So when we're writing out the total delta H of this reaction at temperature T, what we're writing is, well, the coefficient of your product C, H naught, M, T of substance C. So again, what does these terms mean, right? So C here, that is our coefficient. And this H naught MT means it's a molar enthalpy of substance C. That's a big C. So this M here stands for the molar at temperature T. And we can finish this equation by writing out the rest of it. That's small d coefficient times the molar enthalpy of substance D minus coefficient A, the molar enthalpy of A minus coefficient B, molar enthalpy of substance B. Right, so what we have here, we have C and D, these are our products, and A and B are our reactants. Or if we use the general format we defined in our last lecture, what it means is for any reaction, we can write as like 0 goes to the sum of your stoichiometric coefficient times that specific substance I. Right, so if we have that general format of reaction, we can rewrite the general format for our standard enthalpy of reaction as delta HT equals to the summation of mu I and the molar enthalpy delta H naught M at certain temperature T for that specific substance. And just to refresh your memory, when we talk about the stoichiometry coefficient, it's positive for product and negative for reactant. All right. And now the question becomes, how do we find, or how can we what's the easiest way for us to find out what is the molar enthalpy of a specific substance? And the way to think about it is to first define our standard enthalpy of formation, or delta F H naught T. So what it means, again, a standard enthalpy of formation is saying the enthalpy change when 1 mole of pure substance is formed from its elements in relevant form. So let's do an example here. So let's assume we have temperature equals to 307 K. We have P naught equals to 1 bar. Right, so that's our standard pressure. And we're assuming all gases are ideal. So if we're talking about, for example, the formation of formaldehyde, so H2CO, which is a gas, we want to find the delta H, the delta formation of formaldehyde at 307 K. What we need is to find out what are the elements needed to form our formaldehyde. So you can find that in your thermodynamic table, and in this case, the relevant form of that pure substance like carbon is going to be your carbon in graphite solid. Plus hydrogen in its gas form, ideal, plus 1/2 of oxygen in its ideal form. All right. And know how to write it out is also something you may want to practice on. And then we can use our standard enthalpy of formation, which is often write as delta F H naught T, to calculate the standard enthalpy of a reaction. So back to our reaction, like AA plus BB equals to CC plus DD here. What we want is this reaction, number 1. So you can imagine this reaction taking place via a different path. So remember, our enthalpy is a state function. So as long as we start and end at the same initial and final state, the path shouldn't matter. So what we can say is, let's build a hypothetical path where your reactant first goes to its elemental state, and your product will then be formed from their elemental state. So in this case, when we're talking about the process of your AABB goes to its elemental state, we're talking about the reversible process of the standard formation, heat of formation. So we have the delta H naught T for this reaction 2 equals to negative A, the standard enthalpy of formation of substance A, minus B times the standard enthalpy of formation of substance B. 3 here then will become the heat of formation of the product, which equals to C times the heat of formation of enthalpy of substance C, plus coefficient D times your heat of formation of this enthalpy D. Right, and at the end, we have our final reaction, what we want, which is our process 1. That's delta H naught T1 equals to delta H naught T2 plus delta H naught T3. So in this process, we're actually using what we call the Hess law. So we're starting from here to here, and you have like two different ways to go there. And taking together, what we can write as a general form is delta H naught of any reaction equals to the summation of all the stoichiometric coefficient mu I times the heat of formation of that substance I at temperature T. All right, so far what we did is we went over the definition of the standard enthalpy of reaction and the standard enthalpy of formation, and then we built a link between these two standard heats of standard enthalpies. Now, typically, you can find the standard enthalpy of formation from a thermodynamic table, and let's see how do we use it. So here is one of the exercise in your textbook. Let's read it together. It says use appendix data to find delta H naught 298 for the combustion of 1 mole of sucrose, which molecular formula is given as C12H22O11 is a solid. And we're talking about the combustion reaction of sucrose to carbon dioxide and water liquid. Now I rewrite the information from the appendix data, appendix table for you. Now, first of all, we need to write a balanced chemical reaction for 1 mole of sucrose to burn with oxygen. So we can write that as C12H22O11, which is a solid, plus 12 oxygen goes to 12 CO2 gas, oxygen gas, plus 11 H2O liquid. Now, I don't pretend we need to spend time in how to write balanced chemical reaction here. You should have practiced that in Gen Chem. If you forgot how to do that quickly, I hope you can quickly refresh your memory with some practices. And then what we're using is the equation we just defined here, right? We're talking about the delta H of, we're talking about the addition of all your stoichiometric coefficient times the heat of formation of that specific substance. So for example, in this case, well, the 12, that's the product, that's our first product here, and times the heat of formation of CO2 gas at 298, and you can find that number here, right? So this process is just plugging numbers and find out your final result. Well, I already showed you the answer, but you might want to practice it yourself and compare it with the answer key. So this part is pretty straightforward. Next up, then the question becomes, all right, so we know we can read our standard enthalpy of formation from a thermodynamic table. What about the measurement of the standard enthalpy of formation? How exactly did we measure all these things in the table here? All right, so let's use the reaction of H2 gas plus 1/2 of oxygen gas to form H2O as an example. So the process of the measurement of my delta HF H naught for water is like we start from these reference point, and the delta H formation of this reference state will be 0. What we want to know is how do we change from an initial state. Let's just say our initial state are my H2 gas and 1/2 of O2 gas in their reference state, means they're ideal, and at certain temperature, and also my standard pressure, which is 1 bar, and they're separate. All right, so what our final state will be, let me make some space here. Let's see, let me move this one down a little bit. And what our final state will be our water, which is liquid, at certain temperature, and our standard pressure P0 equals to 1 bar. Now, if our product is a gas, we want to make sure it is our ideal gas, not a real gas. Okay, so let's think about what is happening. In our first step, the difference here, actually, we need to make a transformation between the ideal gas of your actual H2 and of your hypothetical H2 and oxygen gas in its ideal form to a real gas. So let's say our state B will be transferring your ideal gas, transferring the ideal gas to a real gas. So we now have H2 gas and 1/2 of oxygen gas and real at certain temperature and pressure separated. All right, and in this case, that's something we will talk about later. Next one will be our state C. That is the mixing of your hydrogen gas and your oxygen gas. At some temperature and your standard pressure, T0, T and P0. And this process is something you can measure experimentally. And then the next step will be changing of your enthalpy to a set of different temperature and pressure. The equation we're going to be used is given here, where delta H equals to integral of Cp dt from T1 to T2, and also from P1 to P2, that's V minus TV alpha. That's something you might want to refresh your memory on if you forgot how that comes from. So the point here is normally when we're measuring the heat of the reaction, we can't do it at any temperature and only at the standard state, right? So what we want to do is, for example, when we're having like a combustion reaction taking place, we might want to have this gas to be in a highly pressured form. So for example, if we want to measure a combustion reaction, we want the pressure to be large. So that means we want to bring our gas mixture from a relatively low pressure standard state to a different temperature and pressure where we can measure the heat of the reaction. So in our state D, we have our mixed H2 gas and oxygen gas at new temperature, let's say T prime and P prime. The next step here is called 4, and 4 is something we will go over in detail. That is to measure delta H for the reaction in which the compound is formed from the mixed element. So in this case, after step 4, we have our reaction taking place. And instead of having a mixed gas of hydrogen and oxygen, we now get to our product, which is water liquids. And what we have is still as a new T prime and P prime. And at the end, we can get it back to our standard state, transfer it back to our standard state. So we have H2O liquid in our original T we want, and also P naught equals to 1 bar. So if we're talking about a gas phase molecule, and then we have to transfer that back to ideal gas from real gas, but now we're talking about liquid water, so we don't have to do that transformation. So in the rest of this lecture, we went over 3 different concepts. The first one is to talk about the calorimetry. All right, so this is the first topic we will cover today. And then we want to talk about the process between your initial state A all the way to final state, and how come this whole processes gives us the difference. So this one we'll talk about Hess law. And at the very end, we will talk about how do we take consideration of the difference between your ideal gas and your real gas. So we have 3 goals for the rest of the lecture today. All right. Next topic here, the first topic we have is the calorimetry, or the measurement of heat of combustion. So here's the setup. Let's just slowly go over this setup. All right, so what we want in here is, first of all, we have this, what we call a bomb that is having the constant volume that is surrounded by a rigid wall that is not going to change. So when we talk about the volume, we're talking about what we have here, right? We're talking about combustion reaction with oxygen gas, and the volume of this bomb is remain constant. Now it contains both your reactant and product, depending on the state of your reaction. In here, for example, if we're talking about a combustion reaction, you have some kind of sample pellet here, let's say a carbon graphite in here. And you have ignition wires, so that upon ignition, you will have the carbon start to react with your oxygen gas. And surrounding our bomb, we have a water bath. And by measuring the temperature difference of the water bath, we get an idea about how much heat has been released from the reaction. So here we have the thermometer to monitor the temperature difference. And obviously, when we talk about the bomb here, these walls are thermally conducting. All right, so for a typical, let's look at a typical calorimetry reaction and see how does it actually measure the heat of combustion of a reaction. So what we have here, in the initial state, we have reactant and water bath at our room temperature, 298 Kelvin. It can be other temperature, it just typically people set it to 298 Kelvin. In our final state, our reactants are being fully consumed to form the product, and again we have our water bath K. All right, and in the process of the reaction, we have the change of delta T. So the temperature, the final temperature will change. So if we consider the system being our bomb plus water bath K, what we have in this process is that your bomb and water bath are surrounded by thermally insulated wall or adiabatic walls. So these are adiabatic walls. So for this process, let's think about the internal energy change before and after the reaction, right? According to the first law of thermodynamics, we have delta U equals to Q plus W. So for our system, we have our bomb plus water bath are isolated from the surrounding. So our Q equals to 0. And in this reaction, we're given this one, the water bath is surrounded by rigid walls. So it does not move. Or what we have is change of volume equals to 0. So in this process, the total change of internal energy equals to 0. But this is not what we want, right? What we want is the product plus water bath at temperature 298 Kelvin, not at this 298 plus some random delta T temperature. So we take consideration between the final state and our desired state using the relationship of change of internal energy equals to the negative C K plus P delta T. So here the C K plus P, that's the heat capacity. Of your water bath K plus product. So we can get delta U at 298 degrees. So that's the general setup. But let's look at an example problem together and hopefully it will start to make more sense. Let's imagine we're talking about the combustion of about 2.016 gram of solid glucose, so C6H12O6, at 25 degrees Celsius. In an adiabatic bomb calorimeter with heat capacity of 9550 joule per Kelvin. So this one is giving us the heat capacity, or what we want is our C K plus P in this case. And in the process, we have a temperature rise of 3.282 degrees Celsius. So effectively, what we end up having is the delta U naught 298 equals to negative of the heat capacity of your calorimeter times the change of temperature. All right, and in this case, what we have is negative 9550 joule per Kelvin times an increase of 3.282 Kelvin. And the result is about negative 31.3 kilojoule. But what we want is the delta U C here. So this subscription C is telling you it's relatively similar to the molar change of internal energy. So we're talking about the delta U of 1 mole of glucose. And you can do that by what we calculated, negative 31.3 kilojoule, and that is for 2.016 gram. And on the top, we have the molecular weight of glucose, which is about 180 gram per mole. And our unit cancel out. And we end up having negative 2801 kilojoule per mole. All right, so what we just did here is using the setup of calorimeter to calculate what is the internal energy change for a given amount of reaction taking place in that calorimeter. But that's the delta U, right? What we want is delta H, or the enthalpy of the reaction. So we're gonna use the definition of our enthalpy here. So H is by definition equals to internal energy plus PV. Now, if we're talking about standard situation, standard condition, you have delta H naught equals to delta U naught plus P naught delta V naught. So every time you see this little superscription, what we're talking about is that it's at standard state. So in this case, let's simplify our life a little bit. So this delta V naught is negligible for reaction not involving gases. And for reaction involving gases, now the standard state for the gases are ideal. You say are ideal. Well, is, because it's just one standard state. So what we have is V naught equals to nRT over P naught, or what we can write is delta H naught equals to delta U naught plus nRT naught times P over P naught times P naught. And these two cancel out. What we have is delta U plus nRT. Wait, so this one. And in this case, when we're talking about the delta N, we're specifically referring to the change of gas, number of moles of gases. All right, and let's look at an example here. So the question reads, for a reaction, well, for this specific substance, CF2Cl, CF2Cl, I don't pretend to remember the nomenclature of this gas, we have its heat of formation equals to negative 890.4 kilojoule per mole. And we're asking to find the delta F heat of, well, the internal energy of formation of this molecule. So again, what we're talking about is the difference between the standard enthalpy of formation versus the standard internal energy change of formation. So whenever we involve a reaction, let's always write the formation reaction here, that involving elemental form as reactant and this molecule as our final product. So what we have 2 carbon, so 2C graphite plus 2 chlorine, which the elemental form is Cl2 gases, and well, 4 fluorine, so 2 fluorine, 2F2 goes to the product. CF2Cl, CF2Cl. It's gas phase, gas form. So the difference between my delta H and my delta U is the change of number of mole of gases. So what do we have? The change of number of mole of gases per mole of reaction. On the right hand side we have 1. On the left hand side we have, well, 1, 2, 3. Right, so your graphite carbon is solid and we don't count that. So the total change is -2. You can plug in the numbers here. So delta U naught, that's equals to delta H naught minus delta Ng RT per mole of reaction. Then plug in the numbers here, negative 890.4 kilojoule per mole minus 2 times RT. So if we're using the same R here in kilojoule per mole, on the top we have kilojoule per mole. Kilojoule. You do that calculation, you end up getting negative 885.4 kilojoule per mole, which is the same answer here. All right, so let me pause here for a little bit. What do we find out today? So we start by looking at the definition of the standard enthalpy of reaction, the standard enthalpy of formation, and introducing the idea of standard state for pure substances. All right, so then we went over talking about the relationship between the standard enthalpy of formation and how to use the standard enthalpy of formation to calculate the how to use the standard enthalpy of formation to calculate the standard enthalpy of a given reaction. We did some exercises together on that topic, and then we carefully went over a process that's needed for us to measure the standard heat of formation or standard enthalpy of formation. So we went over carefully using the formation of water as an example. That's like, how do we take every step to find out the heat of formation for water molecule? Some of them we already know, right? So like calculating the change of state. These are the things we already know. And then we spend some time talk about how to measure the delta H of a reaction using calorimetry. So that's our number 4 here. So far number 4 is known, number 5 is known, number 3 is known. We introduce the idea of calorimetry. That's how to measure the heat of combustion using a setup here. So one of the things I expect you to know is, for example, if we give you this diagram, this setup for a calorimeter, you should be able to tell like what does each part mean. Like if I highlight this part in the exam, you should know, okay, so that is the water bath that's kept, that we're measuring its temperatures throughout the process. Or like if we select these walls, you should be able to tell, okay, these walls are adiabatic rigid walls in a calorimeter. Then we discuss the process of calorimetry. That means we start from the initial state to the final state. And from initial state to the final state, the delta U equals to 0. All right, but we don't want the initial state to the final state. We want to know what is your product and water bath at that temperature we desired, which is 298 K. And we went over how to use the equation we learned before to address for the delta U coming associated with the change of temperature. We went over one example together. And we also went over how to do the conversion between your standard enthalpy of formation and of the reaction and the standard internal energy of the reaction or formation. And we went over one example here together. I'm afraid I'm running out of time, so our next lecture will pick up here from Hess's law, and then we will talk about how to address the difference between ideal gases and real gases in our next lecture. We'll also find some time to talk about the temperature dependence of reaction heat. All right, and that's all from me, and I wish you good luck. And if you have any questions regarding today's lecture, Qing Yang will be with you tomorrow for Q&A session. All right, bye-bye.